Hello and a warm welcome to the Vector Virtual Week 2020. I'm Florian Sommer, and at Vector I'm in charge for business development of the product line embedded software. For all tools that we offer around this is the DaVinci Configurator, Developer, the Timing Architect tool suite, and Base Labs Create Embedded. Today I would like to give you a brief introduction into the runtime analysis for AUTOSAR embedded projects. First of all, I'll talk about the motivation and give you an example when a runtime analysis could be relevant. What you have in many projects is that you have different software components and they all have to be integrated within one control unit and run on this. Now, frequently, developers realize only at a very late stage in the project that they have runtime problems, which manifest, for example, that some functional tests fail, or they manifest in the way that the runtime in the control unit is quite high and you use almost 100% CPU load. And then you face the challenge to figure out what the reason for this is and what you can do against it so that you can fulfill these functional tests or that you can reduce the CPU load a bit to get below a certain threshold. This means the initial situation that we want to address today and the questions we want to answer today is that we have several software components that are to be integrated at almost 100% CPU load. And we want to find out what leads to this high CPU load. And if we now think of a solution, how can we solve this problem and reduce the load? So how can we guarantee that the project advances in the right directions, and how can we prevent new faults at other places whilst we improve the runtime? And to explain all this, I will show you an introduction where we show 3 different classes of timing analysis. But before I do this, I would like to have a look at MicroSAR OS first. Here you can see the different tasks and the different states in which they can be. On the right-hand side, you can see the individual states: preempted, running, suspended, and activated. These are the states a task can be in. And on the left-hand side, you will see a log in a moment, which just shows the current time and which task is changing its status into which state. And at the bottom, you will see a graphic visualization how these task state transitions look like. So now we have a task which is activated at the time of 1 millisecond. This means it's activated, but it's not running on the core yet, because at present there's another task with a higher priority that is running on the same core. At the time of 2 milliseconds, the task is running, and therefore it changes the state into running. At the time of 3 milliseconds, the task is preempted, which means it's interrupted because another task with a higher priority takes up the runtime on the CPU. Then eventually, at the time of 4 milliseconds, the task that we just looked at is resumed. So it's active again, and at the time of 5 milliseconds, it's terminated because it's finished. So this is quite an analyzed analysis which you can get out via a scheduling device. And what you see here is quite an advantage in the analysis, because you can see how long is the complete runtime from activating to terminating, but you can also see that there was a start delay. This means it was activated, but it wasn't running actively. And you can also see that after 3 milliseconds, it was interrupted again by 1 complete millisecond. This means it looks as if the overall runtime would be 4 milliseconds, but as a matter of fact, the net runtime is only 2 milliseconds. And this can make quite a difference. So let's have a look at the different classes of the real-time analysis. which we can use. The first variant that you can select is sampling. This means at specific times and specific periods, I have a look at which task is currently activated. This gives me a more or less accurate result and information on what is running when. Of course, this depends on the sampling rate. An alternative option, which is frequently used, is that you just, during activation and termination of a task, you toggle a pin. And then you can see on the scope meter how long the actual runtime of the task is. So we take it as an example for the sampling. The next category is statistics. Here you can calculate the minimum, maximum, and average runtime of a task. And then you can document these values, and therefore you know how much runtime a specific task has used in this area. It becomes a bit more detailed in the third class, which is the timeline. Here you can determine specific metrics like a net execution time, start delay, and all this can be evaluated in detail. And you can also determine the requirements for the system. In the next step, we start sampling, then statistics, and then the timeline. And we can see which level of detail you can get and which pieces of information you can get out of these individual analysis classes. So we start with sampling. And as I mentioned earlier on, this is frequently used because it's a rather simple procedure. We toggle one pin with the activation of a task, and when the task is terminated, the pin is deactivated again. And we record all this on the scope meter, which gives us a curve that looks like this. So always when we have a high signal, the task is between activation and termination. The pro of this procedure is that the equipment is usually available. You just need a scope meter. And apart from this, you have to set instrumentations in the code to toggle the pin. And then you get this analysis result. In most cases, it's actually used to measure the idle task to see that you have 100% CPU load, as we saw at the beginning. The downside is that the options of analysis are quite small. You cannot see any preemptions. You can see no details. You cannot do it for too many tasks. And the code needs to be removed manually. And if I wanted to do this for a large number of tasks to get a detailed image, then it becomes quite elaborate. And at the end, I also have to keep in mind that I remove the instrumentation in the code again. So much on sampling. Now we go to statistics. We can get this statistic out of the control unit by using GNU AMD. GNU AMD can trigger in the cluster AUTOSAR monitoring and debugging. It can trigger the module VRTM, that's the runtime management. And this module can start a measurement over a time X to generate runtime statistics. The RTM then logs the runtimes on the target. So every time when the task is activated, the runtime is logged. And at the end of the measuring period, it calculates the average value out of it. And it also puts out the minimum and the maximum runtime, as well as the CPU load that has come up within this time frame. This means the output value, which we get in this approach, is what you see here in the table on the bottom right. This means you just see the statistical values, and you have no reference to the time of activation or termination. Now, the pros here are evident. I need no hardware support at all. I don't need a debugger or any evaluation device. I can just do that on the target. And I have a tool support which allows easy configuration. Now the disadvantages here are that I have no details. I only get the statistical values, and I only have a limited time frame that I can look at. This means if I see these results, I don't know how these 25% CPU load have come about. It could be that it's not as indicated here in the diagram that the task is running over the entire measuring period, but it could also be that, for example, in the first 50% of the measuring period, the task is continuously running, and therefore over the overall period, it has an average of 25% runtime. But I cannot really evaluate whether the task has behaved the way I would have expected. And that's also for the time before and after the measurement. I have no indication whatsoever whether the runtime behavior will continue the way I measured it here by coincidence. So the options for analysis are quite low, but it is enough to get a feel for the individual task and how they're behaving on the control unit. Now we get to the third level. This is a complete timeline that is recorded via the profiler. And this works like this. In MicroSAR OS, you can configure hooks for the individual tasks that you are interested in. And for these tasks, you can configure the OS hooks. This passes on the information to the debugger, and it will be configured so that the state transitions are also recorded in a trace. And this trace can then be imported into the TA tool suite, and here you can analyze the trace. Here in this example, I show you a measurement of a task together with this image of the scope meter that we had earlier on. And here you can clearly see the activation and termination time I've seen before on the scope meter, but what I get as additional information is that I can see this task was actually not running so long. The net runtime of the task is not long, but the task is just interrupted. Every time it's called up, it's interrupted by another task which has a higher priority. And therefore you have the long overall runtime. This is a piece of information which is really helpful if you want to analyze these issues in detail. Now, the downside of this procedure is that you depend very much on the hardware. In the first step, I need a profiling option to be able to record these traces. And beyond this, I need an eval device of the microcontroller, which is also supporting tracing. And of course, initially you have the configuration time to configure the OS hooks for the task I'm interested in. But the advantages of the solutions is that I have the tool support to go through the configuration, and I have a much higher detail level, so I can really look at detailed requirements, and based on the timeline I can check whether they have been met. And through the tool support I can also automate it completely so that the initial configuration time that I spend doesn't have to be done again and again, but I can reuse it. And in regular intervals I can record a timeline like this and can always re-evaluate it and see whether the last changes that I've made have actually improved the overall runtime behavior. Now, when you talk about these timing requirements, what do we actually mean by that? What can you do with it? Let's say for periodic tasks, I can take the configuration of the periodic task and I can derive which period is the one I want to have. And then I can check it on basis of a requirement, so that I can check it from activate to activate and always get the period between that. Or, for example, I want to make sure that the overall runtime of this task doesn't exceed the period or doesn't exceed 80% of the period, for example. So these are quite generic things, but you can also work project specifically. For example, if you think of event chains. Let's look at this example. We have a task that reads sensor data, and we have another task that processes sensor data, and we have a third task which is controlling an actuator based on the sensor data. Then I want to make sure that the tasks are called up in the right sequence and that this event chain of reading, processing, and activating happens within a specific time frame, let's say within 2 milliseconds. Then I can specify this as the requirement for the event chain, and based on the timeline, I can check that this has really been met. Now let's have a look at the detail levels of a scheduling trace. So what are the options I have? In this example at hand, it's kept quite simply. We see the timeline of only one single task, and in the light green we can see the interruptions of the task. Now, of course, I want to know which task does it interrupt all the time. So I can display also other tasks of the system and record them. This way I can see which task interrupts the one I looked at before. And if I want to go a level deeper, and if I want to know which runnables within the individual tasks are running, they are displayed in blue in this picture, then via the hooks I also have the possibility to instrument the runnables so that I can also record the state transitions for those. And on the runnable level, I can realize which runnables are executed in which sequence within the task. And for the individual runnables, I can also define runtimes. Additionally, I can also run an interference analysis. This is what you see here in the red lines. And these show me, for this task 2 milliseconds, they show me at which point they were interrupted and in which sequence they were interrupted by which other tasks. Based on this, I can now find solutions, for example, changing the offsets between the tasks or to move specific tasks to another core. If you want to integrate this in your project, what does the entire toolchain look like? As I mentioned before, we have the AUTOSAR OS, which has to be configured with the hooks for the tasks you are interested in. This is then flashed on the control unit, and via the OS awareness file, the debugger can be configured in a way that the state transitions are recorded in a trace file. And this trace file can then be imported into the timing architecture's tool suite. And if you combine this with requirements like event chain, task deadlines, or a maximum load that you want to have on the core, then based on this you can evaluate it, and you get it displayed with the interference view, etc. And you can use these requirements to generate reports. For example, for internal information to show the individual requirements, and you can also use it for a customer report, where you perhaps not show so much detail, but just show over a specific time frame how the CPU load is changing within the individual software versions that you generate. I also said earlier on that you can automate the whole procedure and rerun it at any time. And you can, for example, integrate this toolchain into an image system, and then the report is automatically available after every image. And in the timing architecture tool suite, we have workflows. Within the workflows, we have these green boxes, and they are so-called job nodes. And every one of these job nodes is a GUI interaction, which can also be conducted manually. but on the basis of the job nodes, you can automate it. And what this example is doing, first, it gets the DPA file from the DaVinci configurator, and from there it gets all the system descriptions and the ECUs, and then it generates a timing model where you can set the requirements. All this is then combined with the recorded trace, and based on this information, an evaluation is conducted. And at the end, it delivers a timing report that documents this whole procedure. And it also provides an overview for the entire company or for the project. So much about this topic. I hope that I explained it clearly.
Dankeschön.